Welcome to day 14 of the macOS and iOS Security Internals Advent Calendar. Today we were looking at some lldb basics. Showcasing lldb is best done directly on the command line with lldb instead of using slide decks. So to start lldb we just do lldb and now the question is how to use lldb. And for people who have come from GDB, often they are falling back to GDB syntax, and we will see later that lldb actually has aliases to help people migrating. But one of the good things in lldb is like they have a very good help, so you can just write help and it will print out a help about all the comments that exists. But when it comes to a certain comment, for example, let's choose a comment like settings. We can just write help settings and it will give us more information about the parameters of the settings command. We can also write something like help x. X maybe you know from GDB. For examine, when you say help x, you will see that help x is reading memory from current target process. And when you scroll to the very end, you will see that X is an abbreviation for memory read. So that's a helper for people coming from GDB because there's basically a memory read and a memory write that allows us to basically read and write in target memory. You can see that there's a lot of parameters that you may use or not. But whenever you use something, you just look into the help basically. So running and attaching was also similar to GDB. So if you want to run something, we can just run lldb with, for example, bin ls, and then we just say run. And as you can see here, we now have run this. We can also say something like attach. So for this we need a process identifier. So we will just actually we can just say attach Safari. Then attach to the Safari process after a while. Otherwise we would give it a process ID, so you can see process 811 stopped. You see all the other things here. Now you can say continue, and it's now resuming the process. We can say attach 811, yes, and we are attached again, and we say continue again. And that's this. We can try attaching to malloc. So we can now see we have a breakpoint at malloc. We can now, for example, take this address here, say break set -a for this address. We say continue, and this time we broke at this address. We can also set conditional breakpoints. So for example, we might want to set a breakpoint at malloc, but we set the condition that x0, which is the size, must be greater than 10,000. and only then we will break. We have break list. We have a bunch of stuff here, but this year number 3 is the only one that we are interested in, so we can break delete 1, break delete 2, break list, so we only have our conditional breakpoint, so we can continue. So we now have a break here. We can now read the registers, read reg, register read is the comment, and if we now look at x0, we can see, oh, this is bigger than 10,000, so that worked perfectly. Yeah, and if we continue, yeah, that was the only malloc that basically did this. We can run it again, because you saw we had multiple heads to malloc, but this time we have this one here. We read x0, continue, and that's it. So we only broke on the register x0 that was bigger than 10,000. So if we break on something, we can single step through it, like we use step I to step 1 instruction. We can also use just step, then we would step 1 source line if we have source code available. And as you can see, we single step. And now the difference between step E and step and next E is that step E is going through the or into the branches. So we would go now into the branch. So you can see we are now going through the branch. In so far. Let's find, so here we have now a subroutine call, and if we step I again, we will go and go into it. By the way, I'm always pressing just return because that will repeat the last comment. So now we want to actually step over this, so we say next I, and we basically stepped over it, and can say step I again and go single stepping through the rest, and so we return, and yeah, that's basically what we're doing here. And yeah, you might want to know where we were actually executed from, so you can use the backtrace, so bt. When you have more symbols, you can also say bt full, no, bt all, I mean. But in this case, you see basically BT0, you have BT1, BT2, BT3, and you can say how many frames you want to have basically. Yeah, that's the idea. So as I said, you can use let's say we use register read. So we have registers here, and we can, for example, take x4 that looks like a pointer. Let's say x20x at x4, $x4, and we see the memory at x4. We can also say help mem write. You can then see what you want to write. So you can say, for example, mem write $x4, and we want to write 0x01, 0x02, 0x03, 0x04. And now we can read the memory again, and we saw we have actually written into this memory. Yes, so then the next thing is we can also, when we read the registers again, let's for example x21. So we can x21 this. We can now write any other value in there. And when we read it again, you can see we've changed the value. The next thing, of course, is we want to see the code as the program counter, so we can use the normal GDB syntax for here. We see this here, but we can also use the more powerful disassemble command, where we can say -p for the program counter, and let's say we want to read 6 lines, -c6. If we want to have an arbitrary address, like for example this here, we can say -s, this is a starting point, and show me 6 lines, and then it works the same way. And then one macOS specific thing is here image list, where you can basically see all the loaded libraries, where they are in memory, what their UUID is, and so on. Yeah, that's the quite useful way how to use the lldb. So this was meant to be just a simple introduction into lldb, so that you can use it for debugging macOS apps, but also iOS apps. For that, it becomes a little bit more tricky, depending if you want to do remote debugging or debugging on the device. But this is also the basic when you want to do kernel debugging later on.